So here we have the two-dimensional random walk animation that we left off with last time. Kramer and Josh making their way around this lattice. Josh seems to be enjoying this little section of lattice points over here. And I finished by mentioning that there's this proof in mathematics that you can show that a two-dimensional random walker will almost surely return to the origin at some point in their random walk. Like if you let them random walk for an infinite amount of steps, they'll eventually cross through the origin again. While I don't intend to take an infinite number of steps in this video for the sake of time, I do want to test that. So I've made a test code over here. Here again we have our direction function where we're assigning a random direction of right, up, left, or down. This time, instead of having just Kramer and Josh, we're going to invite 200 walkers to the party. So this is like what we did with our one-dimensional random test, a random walk test. We're creating an empty list of walkers, and then we're putting in the value of that walker's position. Now, this time around, that value is a two-dimensional quantity because we've got vector components. So I'm going to go ahead and make it 3D here so that we can easily extend it to 3D later on. So they're all going to start at the origin with a position of 0, 0, 0, and they're all going to move out from there. Let's come back to returned home in a minute to talk about what that is. We're also going to graph their positions, kind of like what we had last time. We're going to graph the magnitude of their position vectors. So we're going to have 200 graphs crawling on the screen. It's going to be awesome. I'm not going to worry about calculating the average just yet. I might do that in the future. I'm not sure yet. So I'm going to leave these in for now. But for right now, we're going to comment them out. So the way we're going to do this is we are going to update the walker's position here. Again, we're going to give them a random step up, down, left, or right. This time we're just going to give them a step size of 1 just because that's a little bit easier. And also that way I can simplify those down to integers here. This is going to help us with our test later on as to whether they have returned home. So let's talk about how we're going to check that now. Actually, let me go ahead. Actually, before I do that, let me show you what this graph is going to end up looking like. So here we go. We're graphing their magnitude. So this is 200 copies of the type of graph that you had in the previous video. So we're graphing 200 walkers' position vector magnitude, and you see we've already got a good number of them passing back through the origin. So every time this one of these graphs dips down to 0 magnitude, we're getting them through the origin. Now we're kind of helping matters along by enforcing that their locations be integers, so that way we don't get, we might get some rounding error where it's a magnitude of 0.001 instead of 0, and that makes it more difficult to keep track of. All right, let's close that. So the way we're going to track whether they've returned home is through this list of logical variables here called returned home. They're all going to start out at false because in their first step, they all take a step away from home, so they all start out not returning home, right? It's impossible for them to return home in the first step. So what we do is each step we're going to check for whether that walker has returned home. So we're going to check for whether the magnitude of their position is less than some tolerance. When I was testing this earlier, I got a little bit paranoid about testing whether this was equal to 0 because there's always that possibility of rounding error. So we're just going to set this to a tolerance. So basically if they get within 0.1 of the origin, so that's 1/10 of a step size, then we're going to call that at the origin. And of course, we're also reducing the likelihood of that error happening by using this integer function here. But just in case, I don't want to think I've proven the mathematicians wrong on a coding technicality. So I'm taking every precaution here. Then basically, if they return to the origin, then we set that walker's returned home value to true. And here we've got our graph that we had before. And then at the end, so we're going to let this run for 10,000 steps. So I'm going to hit, when I hit run in a minute, I'm going to go take a little stroll around or something, and then I'll speed up the video in post. But basically, after those 10,000 steps, we're going to count the number that ever returned home. So all a walker has to do is return to the origin once, and their returned home value will be true. So basically, if this thing is true, if they ever returned home, even just once, then we're going to add the number that returned to 1. We're going to add 1 to the number that returned. We're going to increase it by 1. Notice I don't need to keep track of how many times an individual walker returns home. I just need to keep track of whether an individual walker ever returned home, because that's what the proof says. And here we have a print statement that's going to give me the percentage of the walkers that returned home. So we're going to hit Control 2. We're going to watch a fun graph animate, and I'm going to put this thing into fast motion so that you don't have to watch it all day. All right, we reached our 10,000th step. So you can see every time one of these touches 0, that's a random walker returning to the origin. And we got 73.5% that returned home. So that's pretty high. You can let this run for longer and watch that number grow. And when I've tested it, it doesn't grow a whole lot. So when I tested this earlier, I think I did it was 1,000 steps, and it was 70% of them returned home. So you don't get a whole lot of improvement for a whole lot of increase, but it does eventually happen. So it's a neat way to kind of visualize and prove this, or demonstrate, excuse me, this thing that the mathematicians have proved. So that's some fun with random walking in 2D. Next time we're going to extend our code into 3 dimensions. So we'll have a lot of fun then. Thank you so much for watching. I'll see you next time. Bye-bye.